Hello everyone, welcome back to our lectures for Geography 101 Earth Systems. Today we're going to be talking all about soils. So soils are definitely an important part of the natural world. They dictate where we can live, the plants and animals that live there, and other things such as landslides and natural phenomena that can have big impacts on society. So the dad jokes will continue as well as the memes. So hopefully you found them at least a little bit amusing. We are going to be talking about soil. So soil science is a science that has quite a lot of literature to it and deserves some respect. So we're going to be calling it soil instead of dirt throughout this course. So soil is composed 50%, usually around 50%, of just water and air. So it's got void spaces in it, and those void spaces can be filled with water or it can be dried out, depending on if it's above or below the water table or it's experiencing evaporation. And so most of the composition of soil is just void spaces that get filled or not filled with water. The remaining composition of soil is majority mineral particles, like the minerals of quartz and carbonates that we've talked about in the previous lecture. And then 5%, depending on the type of soil, is organic matter. And we'll talk about that too in a bit. So those void spaces make up the porosity. So porosity is the amount of empty space in a soil or some substrate compared to the total volume of the material. And so, for example, this material has a lot of empty space, and so it has high porosity, whereas this one has less, and so it has lower porosity. And we can measure this by getting a known volume of material, drying it out, and then filling it with water until it's completely saturated. And that water volume will be the volume of the pores within the soil. And then we can unplug it and figure out how quickly that water drains out in order to get the hydraulic conductivity as well. So the mineral composition of soil depends on the parent material that it's made from, but you can see some different soil types and their different composition. So they're mainly composed of different oxides. So silica or quartz making up the large majority of the material, and then followed by other oxides such as aluminum oxide, iron oxide, calcium oxide, potassium oxide, and so on in smaller and smaller percentages. The remaining material in soil is soil organic matter. These are components of the soil with carbon chains associated with them, their chemical structure. And you can see here the distribution of normal soil and what that organic matter is composed of. So living organisms are organic matter all the same. So worms and bugs and bacteria make up a little less than 5% of the composition of the organic matter, followed by fresh residue. This is like twigs or roots that have recently died and not experienced much decomposition yet. Then you have decomposing organic matter, or the active fraction. And this is the residue that has undergone some amount of decomposing. So it's no longer really resembles the original stem or root and is more broken down, but still has a lot of its cell structures and organelle still intact. And then you have stabilized organic matter, or humus, as we like to call, not the delicious Middle Eastern treat, but this is organic matter that has been thoroughly broken down, and so it's just a slurry or of organic carbon compounds. And these compounds tend to latch on to soil particles and can stay in the soil for a fairly long time. The soil organic matter has a lot of important functions in the soil. It can provide a food source, an energy source for the organisms that live there, as well as providing essential physical and chemical processes. Soil has a function of buffering the pH of soil, which is really important for soil health, and providing cations for different biological processes, and also can help stabilize the soil. So soils with more organic matter tend to erode a little bit less easily, and because soil organic matter is so good at absorbing water, then the water retention is higher, and plants can use that water for a longer period of time. Additionally, soils with higher organic matter tend to not fluctuate in temperature as much. The water that it retains has high thermal inertia, and so the temperature becomes more moderate in high organic matter soils. So there's a number of different functions that are really important that the soil organic matter can do. So you can see here that soils really are helped out by soil organic matter. For example, we can go back to that water retention. So for every 1% increase in organic matter, you're saving 25,000 gallons of soil water per acre that can be now absorbed. So sometimes if a farmer wants to reduce the amount of water that he's using on their crops, then it can be more efficient to try to increase the soil organic matter than try to just increase the water supply that he's irrigating his cropland. So here you can see the different progression from fresh residues to stable organic matter or humus. And so this process can take several years to occur. And throughout that process, you have organisms shredding the material and breaking it down, and in turn releasing carbon dioxide into the soil. And so you can see that it can take a fairly long time for that organic matter to finally get fixed to the soil and move from its original state of a dead twig, for example, into that organic matter slurry. The food webs and the different organisms within the soil are fairly complex. Soils are some of the most diverse ecosystems on our planet, and they can have multiple different trophic levels or levels to their food webs. Starting with the first trophic level, the photosynthesizers, such as the plants that are growing and absorbing sunlight and growing roots into the soil. And you have the second trophic level, which is the decomposers. Those are the bacteria and the fungi that are growing and eating those photosynthesizers. And then the third trophic layer are animals that eat the second trophic layer. So these are arthropods, nematodes, and larger bacteria that can eat the smaller bacteria. And then as you move higher and higher up, you get into predators in the fourth and fifth trophic level, such as birds and gophers. So each of these different organisms serve a very helpful purpose to the soil. They can shred material and make it more easy for bacteria to break down and form organic matter. They can act as nitrogen fixers. A lot of bacteria are really important for making sure that plants have enough nitrogen available for growth. And so really it's an ecosystem, and it requires all these different organisms in order to function. And so there can be a lot of organisms within a small amount of soil. For example, there can be roughly a billion bacteria within a single tablespoon of soil. So it's nothing to scoff at. And there can be several hundred nematodes or smaller worms that are in that tablespoon as well. And so yeah, there's a lot of different organisms and with high density in productive soils. So the next concept that we're going to be talking about is soil horizons. So soil horizons are layers in mature soil that develop through processes including leaching, decomposition, and weathering. So you can see here, these are the different layers that develop in a soil, and we'll talk about each of them. And so there are 6 different types of soil horizons. So there's the A horizon, the O horizon, the A horizon, E horizon, B, C, and R. And so the O horizon is short for the organic layer horizon. So it's composed of the grasses and roots and the recently fallen leaves and all of the fresh, recently dead or living organic matter that composes the soil. Next, we have the A horizon, which is also known as topsoil. So if you go and buy a bag of topsoil, it's going to most likely be from a soil, and it's A horizon. And so this is the horizon that has, it's a soil that has large amounts of organic matter in it, and so it generally has this darker color, and it's just decomposing the organic matter in the O horizon just immediately above it. Below the A horizon, sometimes we can get an E horizon. E horizon is short for alluviation horizon, and this is a horizon that's experienced extensive leaching. So the organic matter that was once formed in it has had water flow through it, or some other fluid that's caused a lot of those nutrients to be leached out and deposited below it. So generally the E horizon has this pale color to it, sometimes a bright white like this, just because all of those nutrients have been leached away, and what's resulting is usually smaller clay particles after a lot of the minerals have decomposed and hydrated as well. You can see here's another example of a fairly large E horizon. This is when acids actually were the leaching agent and changed the color of the soil. Next, we have the B horizon, also known as the subsoil. So the B horizon is below the E horizon, and it's composed of that soil, which is has a lot of broken down rocks, but can have some larger rocks as well, and it's where all of the nutrients from the E horizon get leached down into. And so you can still have those dark colors associated with the B horizon. And it kind of, the bottom of the B horizon kind of signifies the end of the what we would normally call a soil. And so the solemn is the combination of the O, A, E, and B horizons. And this is kind of known as the true soil, the soil that's not just made mainly of rock. So below the solum, below the B horizon, we have the C horizon, which is also we talked about regolith. So it's the partially weathered bedrock. So this has heavy concentrations of large boulders and rocks that have not undergone extensive weathering and are just on the process of becoming a true soil. And then below that we have bedrock, or the R horizon, the rock horizon. And so that's the parent material that all of the soil was originally made from. And so that bedrock is just the rock in which the soil is formed from. And so the bedrock can be at quite a far distance below the above horizons, but sometimes for a newer soil you can also get the bedrock just below the surface as well. So those are the soil horizons. The A and O horizon that make up the topsoil, along with the E and B that make up the solum, and then the C and the R horizons, which make up the more rock-rich layers. Next, we're going to talk about soil color. Color is very important for diagnosing the health of a soil, the nutrients in it, and what kind of chemistry we can tell fairly easily by just looking at the color. So you can see here, this is a map of the United States showing the different soil colors at different depths. And so the soils can change colors with depths as well as with space laterally. So we judge the color of a soil using the Munsell color scale. And we'll get a little bit into color theory here. So the Munsell color scale is a book of colors that are splotches of colors, just like this one, where you can judge the color of a soil particle against these reference colors. And so the Munsell color system is defined by three different numbers. The first one is the hue, which is the what color is it on the rainbow from red to orange, yellow, green, blue, and violet. So those are dictated by these lettering systems here. Next, we have the value, which is how light or dark that color is from dark black to white. And then lastly, we have the chroma, which is how saturated that color is from very faded to a vibrant color. And we can describe all colors using these three values. And we dictate that using this nomenclature here, where we have the hue indicated by a number and letter, we have the value following that letter, and the chroma after a slash after the value. So you can see here, these are all the different hues that are possible. And so it goes more than just red, yellow, green, yellow, green, blue, purple, green, purple, red, purple. We also use these numbering systems to define subcategories within those different designations. For example, a 2.5 R is slightly more purple than a 5 R, whereas a 7.5 R is slightly more yellow than a 5 R. And you can do that for any of the different colors, with for example, the halfway point between red and yellow-orange or orange color is 10R. And so we can go from 2.5 to 10. And so then the value and the chroma are defined by these numbers as well. So the value will go from 1 to 9, with 1 being the darkest colors and 9 being the lightest colors. And then the chroma will go from 1 being incredibly poorly saturated, so very dull colors, to 14. And a lot of times you'll have a chart that will go up by 2s instead of by 1 for a chroma. And so the highest numbers, a chroma 14, would be brilliant red color. So the colors can tell us a lot about the chemistry in that soil. So black soils indicate high organic content. So the blacker the soil, usually the more organic compounds that are contained within it. And so usually you can tell how fertile a soil is based off of how black it is. Red soils, we've talked about previously with iron oxidation, are the result of high iron contents in the soil. So if you see red soils like this, they're usually the result of high iron content that has been exposed to oxygen and formed iron oxide. Yellow soils, like the loess that we talked about previously, can be the result of high concentrations of the mineral goethite, which just like those red-colored rocks is an iron oxide, but goethite is an iron 3 oxide instead, and it produces this yellow color. And then blue soils are more common than you might think, and so they indicate the presence of sulfur. So iron sulfide can produce a yellow color in soils. Next, we're going to be talking about soil pH. So the pH of a soil is really important for making sure that we maintain the soil health. Plants have a hard time growing in pHs that are too high or too low, such as in this case, we have a soil pH of 3.5. And so here is a map of the soil pH throughout the world. And you can see that the pH can vary substantially from very acidic to slightly alkaline. And generally, you have the most acidic soils occurring in areas with heavy rainfall, such as the Amazon rainforest and the Southeast Asia, as well as in tundra climates as well. So generally, you want the soil pH to be between 8.3 and 4.6. So if you have a pH that's too alkaline, then plants have a really hard time growing, mainly because they have a hard time taking up iron. And if you have a soil pH that's too low, then the bacteria have a hard time growing there, and you can't have plant growth with those bacteria fixing the nitrogen. And you can see here different chemical reactions that result in changes in the acidity of a soil. The most common and widespread one is the absorption of carbon dioxide. So like we talked about with ocean acidification, when carbon dioxide enters a soil through the atmosphere or through decomposition of organic matter, remember when you decompose organic matter, then you release carbon dioxide as well. That carbon dioxide can react with the water in the soil and form carbonic acid. And so the more carbon dioxide in the soil, usually the more acidic that soil tends to be because of that carbonic acid that forms. Additionally, you can have ammonia reacting with oxygen. Some bacteria produce ammonia, or sometimes it can be and just used as some type of fertilizer. And so ammonia reacts with oxygen to produce nitric acid, and so that that can also increase the pH of the soil. And then there's a number of different reactions as well, such as reactions of phosphate fertilizers with water that produce acids, as well as iron sulfite, that compound that creates that blue color, reacting with water and oxygen to create sulfuric acid as well. And so obviously as well, you have, if you're pouring acid rain on a soil, the pH is going to increase as well. So these are the different processes that can affect soil pH. And so here you can see how easy it is for plants and bacteria to absorb different nutrients based off of the pH of the soil. And you can see here that, for example, both calcium and iron is really difficult to absorb when you have very alkaline soils, whereas manganese and phosphorus, for example, are harder to absorb at lower pHs. So it's a balancing act, and you really have to try to get what your plants are most needing based off of what's available from the pH. All right, let's take a short break, and afterwards we're going to talk more about different soils and different soil orders. So I will see you guys in a bit.